Hi everybody, hope you're doing well. In previous lectures, we discussed groups and representations of the rotation group in 3 dimensions, which led us to the concept of spin groups. And there is a very important connection between spin and quantum statistics. All right, that's why we need to discuss a little bit more these concepts, which are very important in quantum mechanics. So the spin statistics theorem, I will not derive the theorem here because it demands the use of Lorentz transformations or representations of Lorentz group and relativistic arguments, to be precise perhaps. But first connections were related by Shears and Pauli, Wolfgang Pauli, around 1939, but it was perhaps with a more rigorous treatment demonstrated by Schwinger in the 50s. All right. So, for us to discuss the spin statistics theorem, first of all, we need to consider a very important aspect in quantum mechanics, which is really distinct from the classical physics, all right, or the classical mechanics, which is the concept of identical particles. Okay. And it states that in quantum mechanics, two particles which are identical, for instance, two electrons, cannot be distinguished. So in quantum mechanics, there is a concept of indistinguishability. Particles, identical particles, are not cannot be in many situations cannot be distinguished, or as an example here, they cannot be marked and followed at every instant of time and space. So consider classical situation here first. All right, so it's a, I don't know if you can see properly what I'm showing in the board, right? But first, consider a classical problem here. So classical mechanics is scattering in a classical system. So suppose two rigid spheres or billiards, which you can make to collide with each other, and they scatter. All right. So suppose I have an initial ball here or sphere. I'll call the blue sphere. All right. And I also have a red sphere here. And if you were considering a billiard table, this can be tracked from the beginning of its trajectory to the end. So if they collide at some point, I can always see that this blue sphere collided and produced the final state here. So this is the initial state in the collision with the momentum P1, and this is the momentum P1 primed. All right, so, and the energy, of course, and if the particle has other properties like spin and whatever, I can exactly identify that this blue sphere here, which has a momentum P1 and an energy E1, is the particle which was converted after the collision to the particle in blue, right? So I can track the trajectory at every instant of time at any point in space. Also, of course, at this point they collide. Okay, they collide here. This is the blue, and the red particle followed this trajectory here. So this was the particle with momentum P2 and the energy E2. Probably it has some spin, okay? And this is the red particle or the red sphere colliding with the blue sphere, and they just follow separate trajectories. In classical physics, I can I can follow I can follow each step of the collision. All right, so the blue particle I can follow the trajectory, so the red particle I can follow the trajectory of these particles. I can identify, I can distinguish them because I can paint the sphere. Suppose they are exactly the same object. Suppose they are electrons. Okay, in classical mechanics, I could just paint the first electron blue and the second electron red, and they collide. And this electron in blue is, is the electron which originated the final state in blue. And this electron in red at first is precisely the electron which originated that state in red. So this is for scattering in classical mechanics. But in quantum mechanics, it is not possible, all right? You can have asymptotically two. So in quantum mechanics, let us see what happens for indistinguishable particles, okay? For identical particles. So in quantum mechanics, what happens in such a scattering process? Okay, we have a first particle, which I will call the blue particle, right? And I have the red particle. They are identical. I cannot distinguish, but if they are largely separated, if they are distant in space, at first I can say this is the blue electron, and this the second here is the red electron. For electrons, it could be photons, it could be any other particle which is identical to another. For instance, two protons, two neutrons, two electrons, two neutrinos, identical particles in quantum mechanics. I can make them collide. Let me make it differently here, but it's the same idea of a collision. All right. So suppose this blue electron is moving to the right, and there is a second electron, which is red here, is moving to the left. So this is the electron with momentum P2, which corresponds to some energy. Of course, I will just write momentum here. And this is the electron with momentum P1, and they move towards each other in a collision experiment, in a scattering. And at the end, I see that there is some electron with momentum P1 primed and a second electron with momentum P2 primed. This goes here and that goes to that part of the graph. But I don't know if this electron produced that or this electron produced that. In classical mechanics, I could eventually say, okay, this collision followed the following trajectories for the particles. Okay, they get close together, they repel each other because there are Coulombic forces here, so they interact in some region here. But if it would classical mechanics, I would say, well, the electron in blue produced this state, this final state here, and the electron in red produced this final state here. But I cannot know that. I just know asymptotic states. So this is one possibility. The electron 1 initially produced the electron 1 primed in the final state, and the electron 2 produced the electron 2 primed in the final state, or it could happen that way in the second possibility. So this is the first electron, P1. This is the second electron here. So this is the P2. And the collision occurred in the following manner. All right, this goes here, producing the P1 primed state, and this here produce the final state P2 prime. So the electron 1 produced the 2 prime state, and the electron 2 produced the 1 prime state. So in the middle of the event of the scattering, something happened here. And there are two possibilities. Okay, I cannot distinguish between these two possibilities because in quantum mechanics, the uncertainty principles will not allow me to exactly know what happens when these two electrons are close enough. Okay, because I need to choose. And if I'm choosing to know exactly what happens in momentum for the initial and final states, I cannot know everything about the exact position of each electrons. So when they are close together, they interact by Coulomb repulsion, electromagnetic interactions if the process is relativistic. So magnetic fields also play a role here. And it is said that the two electrons exchange a virtual photon. Okay, but this is a virtual particle. Doesn't matter for the moment. It can be for non-relativistic electrons. Okay, so the two electrons, when they collide, I only can know the initial states. The initial states are P1 and P2. All right, and the final states I also can measure because the initial states, two particles are far apart, so they start very distant from each other, and they are in a collider, in a particle accelerator. They are made to collide, so at the initial time, instant of time, both of these particles have a definite momentum energy, and when they collide, I cannot know if this blue produced the final state there and the red produced the final state here, or in the collision, if this produced the final state there and this produced the final state here. Okay, so these two graphs, okay, these two processes are probabilistic, and the amplitudes of these graphs, okay, this process and that process interact, interfering with each other, okay, and the sign of the interference may be positive, so these two graphs may add or they subtract. All right, if they are electrons in my example, the sign between these two graphs, these two, which you can calculate, these two amplitudes for these graphs, these processes here, must be a minus, okay, if they are electrons. But if it were other particles with spin in integer spin, the sign would be plus. Suppose two charged mesons with spin 0 or spin 1, they could interact, and these two processes, which are probabilistic, I cannot know if the electron 1 produces the electron 1 primed, or if the electron 1 produces the electron 2 primed. I cannot know that. There are probabilities for these two graphs. Okay? But if electrons, these two graphs, interfere destructively, if non-electrons, if particles with spin integer spin, they interfere constructively, they add up in a constructive manner. Okay, so particles, not only electrons, but particles which have half integer spins, these processes interfere with the minus sign. And for particles with integer spins, they interfere with the plus sign. Particles with half integer spins are said to be fermions, and particles which carry an integer spin are called bosons, because they follow different rules in scattering processes and in all the processes in quantum mechanics. And the statistics also differ from one type of particle to the other type of particle. Okay, and the spin statistics theorem is about that, about the way these graphs must be considered and the way the particles obey some kind of statistics. All right, and that's what we will need to discuss a little bit more. All right, so in quantum mechanics, if you pick up two electrons at the starting point, you cannot know what electron produced the final states. You cannot know that. All right, and this is a very striking feature of quantum mechanics, but because in classical mechanics you would just color the first electron blue and follow the trajectory, and the second electron red and follow the trajectory. But in quantum mechanics, you cannot follow precisely the trajectory of the particles. So you don't know what process really occurred in a scattering. So there are probabilities of this thing and that thing, and they interfere, or destructively or constructively, according to the type of particle. If fermions, so this for fermions and this for bosons. Okay, the two names, particles in three-dimensional space, can they can only be fermions and bosons. There is a very intricate situation in two dimensions, but I will not go into that. Okay, in two space dimensions, which is the only situation it can occur, you can have something in between fermions and bosons, and I guess Frank Wilczek called these particles anyons, but they are just quasi-particles in condensed matter system, in solid state systems. And as a matter of fact, really elementary particles can only be fermions or bosons. Okay, there are only two possibilities, and it is related to spin. So here I am anticipating something half integer spin for a fermion. Okay, and this integer spin for a boson. Okay, so bosons are particles with integer spins. Fermions are particles with half integer spins. And the sign in this interference process is plus constructively for bosons, and minus or destructively for fermions. Okay, right. Now let us discuss another important thing. Okay, so let us state first the spin statistics theorem. Okay, so first, boson or bosons, particles with integer spins. Okay, integer spins. So a integer spin can be a particle with 0 spin or 1 or 2 or 3, any integer. Okay, and the projection in the direction of z divided by the h bar would go from minus s plus 1 till you get to s. All right. So examples here. Examples. A Higgs boson which is responsible for attributing mass to some the field of the Higgs field, as a matter of fact, is responsible for attributing mass to some particles, and the quanta of this field are called the Higgs bosons. A Higgs boson has spin 0, a photon which carries electromagnetic interactions has spin 1, a gluon which carry the strong interactions between quarks inside a proton or a neutron, or inside mesons. The quarks interact, okay, for hadrons and all nuclear matter. There are subparticles forming neutrons and protons, which are called the quarks, and quarks interact with each other, exchanging a particle which is the, I will call it, is the photon for the strong interactions, but it's very more complex. But spin of the gluons are described by spin 1, right? And also there is a three types of bosons, which are called the W plus, W minus, and the Z naught or the Z zero, which are responsible for the electroweak interaction. So these particles are also spin 1. So this is electromagnetic, the photon, electromagnetic carrier of interactions. Okay, the gluon is for the chromodynamic interactions or the color charge interactions or the strong interactions. And W plus, minus, and Z naught are responsible for the weak interactions. Gluons are not electrically charged. Photons are not charged under electromagnetism. The Z naught is not charged, is neutral particle under electromagnetic forces, but the W plus and the W minus are charged under electromagnetic interactions. It is a peculiar feature here. And also you can consider the graviton, if it exists. We don't know. Okay, we don't know if a particle mediating gravitational interactions exist. It is not till today. It was not measured experimentally, but they are responsible for, if they exist, They are responsible for the gravitational interactions. Okay, so for elementary particles, we can add to this set of particles another example. So I'll put them here. A phonon. A phonon is a particle responsible for mediating vibrations of a lattice. The ions in a lattice and in a lattice of atoms in a solid, for instance, they can vibrate, and they call it the collective vibrations produce sound waves in a solid, and sound waves can be quantized. The quanta of vibrations or sound waves in a solid are known as phonon, in analogy to the photon. Okay, so they are the quanta of sound waves. There are also the magnons, which corresponds to the quanta of spin waves. Suppose you have a material. In a material you have spins of the atoms, and if the spin of one atom can jiggle a little bit, it can just fluctuate. It transmits the fluctuation to a neighbor spin, and this propagates as a wave in a crystalline material, in a solid state material, and the quanta of these spin waves are known as magnons. Okay, so phonon, magnon, they are particles having integer spin. So phonons, the most trivial phonon has, which corresponds to some longitudinal modes, have a spin 0, okay, and magnons have spin 1, total spin 1, okay, but there are other examples here of particles behaving as bosons. So atoms, which are composite systems, they are composed of electrons and protons and all that, but as an entity, as an entire entity, there are many atoms which can be described by some integer spin, and they are therefore bosons. Okay, so bosons, particles with integer spins. Okay, now let's go to the fermion case. Fermions, all the fermions are particles with half integer spin. So 1/2 or 3/2 or any integer, half integer spin. Okay, and of course the SZ component normalized by the H bar can also go from minus S plus 1 until you reach the final state. So for spin 1/2, which is the basic case of fermion, this normalized component of the spinning direction of Z can only take two values, minus 1/2, minus 1/2 plus 1, which is plus 1/2, and we reached already the maximum possible projection. If you pick a particle with spin 3/2, we can have minus 3/2 for the projection, okay? Minus 3/2, minus 1/2, plus 1/2, and plus 3/2, okay? So in this case, if you perform a Stern-Gerlach experiment here, you will obtain just just two possible measurements. If you measure the spin of a semi or a half integer spin particle, with spin 1/2, you can measure minus half or plus half, all right? If you measure a 3/2 spin particle, you can measure in a Stern-Gerlach type of experiment minus 3/2, minus 1/2, plus 1/2, plus 3/2. So the beam will split into four possibilities. In the case of 1/2, the beam splits into two possibilities. You can do the same reasoning for the integer spins. So for instance, for a spin 0 particle, a beam passing through a Stern-Gerlach experiment will not deflect a particle with by means of spin effects, all right, by means of a intrinsic magnetic dipole effect, all right. And if the particle is a spin 1, the beam will split into three possibles, which are minus 1, 0, and plus 1, and so on and so forth. Okay, so these particles, the fermions, which are semi-integer particles, as examples, we have electrons, okay, electrons, positrons, which are the antiparticles of electrons, electrons and positrons, protons, of course, the antiprotons, protons, neutrons, which internally are composed, they are composed of quarks, okay, and quarks are also fermions. So a proton is a specific particle composed of two or of three quarks internally. A proton is composed of three quarks internally, and the composite particle resulting from that three quarks is a fermion, because of the combination of spins produces a one half particle. So both both examples I am presenting here, all the examples are spin half particles, all right? But there are particles with spin 3/2 or 5/2, mainly in composite systems of many electrons. You can find a complete spin of or angular momentum of 5/2 and 7/2 perhaps. Okay, so electrons, positrons, protons, neutrons, the antiprotons and antineutrons, which are internally composed of quarks, and the antiparticles of antiquarks, the quarks are fermions. Okay, and there are the neutrinos, which are electrically neutral particles with mass nearly zero, and they play a very important role in the beta decay and the nuclear processes. Okay, they are weakly interacting particles. I don't know how many neutrinos are passing through us as we are talking about, because neutrinos weakly interact. They are weakly interacting particles, but they have spin 1/2. They are fermions. Okay, and there are many other examples here. You can find out another many examples. And the main aspect of a fermion, okay, the main aspect of a fermion is the following. Fermions, which is the beginning of a statement of the spin statistics theorem, fermions must obey the Pauli exclusion principle. Okay, Pauli exclusion principle. Fermions must obey the Pauli exclusion principle. Bosons do not obey the Pauli exclusion principle, which is due to Wolfgang Pauli. Okay, this scientist discovered this principle, and this principle must be obeyed by fermions. And for bosons, it is not necessary, they do not obey, as a matter of fact. Okay, so you can say fermions don't want to be with each other, they exclude themselves. And by contrast, bosons are more, say, in in formal language, they are more gregary. They are friendly to each other, and they can many bosons can occupy the same state. So Pauli exclusion principle says it that states the following: no more, I can state in many ways, but no more than one fermion can occupy occupy. Yes, I wrote it correctly. No more than one fermion can occupy the same quantum state, which in 3 dimensions of space plus the spin, there are 4 quantum numbers. So for a quantum particle, the state, a state of a particle can be written as the position of the particle and the spin of that particle. Okay, you could write a state in the position space, and in position space there are 4 quantum numbers: x, y, z, and the spin of the particle, which can be plus half or minus half. Or of course you could use atomic orbitals in an atom, so the position is replaced by the atomic orbitals, and there are 3 quantum numbers: the principal, the azimuthal, and the magnetic quantum number. So this is the orbital quantum number, this is principal quantum number, this is the projection and the spin. So there are 4 quantum numbers. There are 4 quantum numbers in 3 dimensions, which corresponds to the position. It could be momentum, of course. You could replace position by another representation, which is momentum. So a state would be represented by the momentum state and the spin state. All right. So there are 3 quantum numbers related to the spatial coordinates, being position or momentum. They are non commuting variables. Okay, so you cannot use simultaneously, but there are 4 quantum numbers in 3 dimensions of space, which are position coordinates or orbital quantum, atomic orbital quantum numbers, or they are momentum and spin, and also spin. So there are 4 quantum numbers. You cannot you cannot put more than one electron in that state. In a state like this one, you can only put one electron, right? From high school, I guess, you must remember that an orbital 1s, which corresponds to the first layer, atomic layer, and s corresponds to L equal to 0, m equal to 0, you can put one electron with spin up. Okay, just one electron with spin up. So this state here corresponds to 4 quantum numbers. 4. N equals to 1, L equals to 0, M equals to 0, spin equals to 1/2. This is the state up. I can only put one electron. The other electron in a 1s orbital, you could put another electron, but this is another quantum state in Hilbert space. This is not the same. It's not the same in the Hilbert space. It is 1, 0, 0, and minus 1/2. Okay, so this state is orthogonal to that. Okay, so I guess everyone already have heard that sentence, which states that two bodies in classical mechanics, two bodies, two objects cannot occupy, two objects cannot occupy the same space. Okay, the same position in space. Okay, they cannot occupy the same space. All right. In quantum mechanics, for fermions, it is valid. It is a valid statement, but your space here means Hilbert space. So rephrasing the classical conclusion, you could say two fermions cannot occupy the same state in Hilbert space. Okay, they cannot occupy the same place in the space, but in the Hilbert space. Okay, and that's what the Pauli exclusion principle really mean. You cannot put two fermions in the same quantum numbers, in the same, say, state or position in Hilbert space. And the Hilbert space is, when represented in the position basis, must have the coordinates x, y, z, and the spin. All right? So you cannot put two electrons in the same x, y, z with the same spin. You could put, probabilistically, two electrons at the same x, y, and z, but one quantum number is missing, which is spin. Quantum particles have spin, and therefore two fermions cannot occupy the same quantum state. You can put no fermion in that state or one fermion in that state, not two, just 0 or 1. This is the possible occupation numbers for fermions. Okay, bosons, you don't need to worry about that. They do not need to obey the Pauli exclusion principle. Right? So no more than one, which means 0 or 1 is the occupation number. Okay, no more than one fermion can occupy the same quantum state, a given quantum state. Perhaps it's better to say a given quantum state. Given this state, 1, 0, 0, 1/2, which means the first layer with L equal to 0, with M equal to 0, with spin equals to 1/2. How many electrons can I put in this state? Or none, or 0, or 1. I cannot put a second electron in this state. But there is another which is orthogonal in Hilbert space, which is not the same state, which is not the same vector in the Hilbert space, which is 1, 0, 0, minus 1/2 in terms of these quantum numbers here, N, L, M, sigma. All right, this is another state. I can put one electron here or none or 0 electrons in that state. Okay, so occupation numbers for fermions. Okay, occupation numbers terms of occupation numbers, which will be important when we will discuss the algebra for bosons and fermions. So fermions versus bosons. Occupation number in a state. For a fermion, I can put n. N will confuse you with the principal quantum number now because, but okay, occupation number. It is not a principal quantum number here. Okay, it's just a number of particles I put in a given quantum state. I can put 0 for a fermion, or I can put 1 fermion at a given state, at a state psi, a given state psi. All right. So a given state in Hilbert space, I can put 0 fermion in that state or 1 fermion in that state. If a particle is a boson, I can put no boson in that state, or 1 or 2 or 3 or 4 or 5 or any integer going to infinity. And this, as a matter of fact, is the origin of a Bose-Einstein condensation. Many bosons condense to the lowest energy level. For fermions, you cannot do that because there are a limit for the number of fermions you can put in a given state. So if a lowest energy level is already occupied, you need and you have more electrons to consider in the system, you cannot put all of them in the lowest level energy state. You can populate, you need to populate that lowest level energy state, and after that is populated by one fermion at each state, you need to move to the next lowest level energy state. If they are bosons, if they were bosons, you could put all the electrons in the same state. But for bosons, you can put any number which you want at a given state in Hilbert space, at a given psi in Hilbert space. All right, this is the very striking difference. Fermions, occupation number 0 or 1. Boson 0, 1, 2, 3. For any integer number of particles, I can put in the same state. All right, so this is exclusion principle. This is not exclusion principle. All right. Now let us discuss another aspect. Okay, another very interesting aspect, which is um, the following. So I can state right now the spin statistics theorem, which is the goal of this lecture. What the spin statistics theorem really says. It says that for half integer spin particles, for half integer spin particles, the Pauli exclusion principle must be satisfied. And as a corollary of that, perhaps, a, and the state of a two fermion because half integer, you can replace it by fermion. For fermions, the Pauli exclusion principle must be satisfied, and the state of a two fermion system must be totally anti-symmetric under permutation, which we will discuss in brief in the following moment. Okay, so if you pick up the state of two fermions, not just only one, each fermion is in one state. But if you exchange them, you permutate the two fermions, the state must reverse sign because state must be totally anti-symmetric. And for the other part of the theorem says that for integer spin particles, which means bosons, okay, which means the bosons, the state, the Pauli exclusion principle need not to be satisfied. For integer spin particles, Pauli exclusion does not apply, and the state, the physical state of two bosons must be totally symmetric under permutation. Under permutation. Okay, this is what the spin statistics theorem says. If you have fermions, you have two fermions, and you have a state corresponding to the quantum state of these two fermions, if you exchange them, if you put the fermion 1 into the slot of fermion 2 and the fermion 2 in the slot of fermion 1, the total wave function must change its sign, while for bosons the sign must remain the same. Okay, and in this case, fermions satisfy the Fermi-Dirac statistics, which we'll discuss in the next lectures. While for bosons, they must satisfy Bose-Einstein statistics, okay, or distributions. So this is what is the spin statistic theorem is about. Now let us consider the following thing. Consider two identical particles. Okay, two identical particles. They have R1 and R2 and R2, sigma 1 and sigma 2. These spin projections can be anything. I am not just considering a fermion. So let me write it as S1 and S2 just to remember the spin projections. And after that, considering two identical particles, suppose it is possible to factorize or to separate the orbital and spin degrees of freedom. Okay, suppose that is possible. So if you write the wave function in the position space, all right, so R1, S1, these are the coordinates, the four quantum numbers of particle 1, R2, S2, which are the four quantum numbers of the particle 2, you suppose that you can separate the variables writing a total function depending on R1 and R2 tensor product, which is just a product of in a tensor sense, because spinors are vectors with the n-dimensional components. And these functions here are space-time functions, which I'm just using space here, space, because I can consider at time t equals to 0, this state, these things evolve in time. And I can just factorize, or I can just separate the variables, position variables and spin, which I'll call the key letter from the Greek alphabet, the key, which is the spin function, depending on S1 and S2, depending on the spins. All right, so if I can do that, okay, what I have for fermions, or, or sorry, let me define a definition here, permutation operator. Permutation operator, which we'll call P. This operator P here, it just makes the following action. It replaces 1 by 2 and 2 by 1. It exchanges, it permutates, it permutes the particles. Okay, so the particle with coordinate R2 will be plugged into the slot of the particle R1 and vice versa. And the same for the spins. Okay, so this is a very easy to do. So suppose you have a permutation of some psi, I'll call simplistically 1 and 2. What it does is some eigenvalue of that operation, of the permutation operator, an eigenvalue, and produces the function of the function in the reverse order. Okay, it permutes, it changes place of the two indices. All right, this is what the permutation does. And in 3 dimensions, there are 2 possible eigenvalues for this operator, which is plus and minus. Okay, there are 2 possibilities. So for bosons, the plus applies, and for fermions, the minus applies. So plus is boson, and the minus is a fermion. Okay, for boson, if you switch places of 2 bosons, the wave function gets nothing, but is just this function with the indices switched. Okay, and the sign here is plus. Okay, but if they are fermions, if you switch places of 2 fermions, the wave function gets a minus. Okay, it is anti-symmetric, it's odd under the permutation. Okay, so bosons are even representations of the permutation group, and fermions are odd representations of the permutation group. Okay, I could put that way. Right, so consider 2 fermions, or two identical particles, and let us analyze first the case of bosons. Okay, for two bosons, suppose you have that, and you can factorize the function. You can rewrite the function as a product of position variables. You could do that for momentum variables here, and you separate the spin variables. Okay, so you are separating spin variables. So for bosons, if you apply the permutation exchanging 1 and 2, okay, permutation changing the indices to a function psi of R1 S1 R2 S2, you are just applying the permutation symbol to both functions here. So you do the following thing. You'll have a phi function of R1, or sorry, R2 R1, compare it to the original function. So you switch the slots here, times a spinor of S2 S1. Okay, so it corresponds, which corresponds to permutating the original coordinate arguments. Okay, so the permutation is a idempotent operator. So if you apply it twice, you get the identity. Okay, this is called the nipotent operator. All right, and it apply. You can distribute the application. So if you apply the operation to the whole wave function, you can apply it to the first times the application on the second. Okay. If you apply the permutation symbol again, you will have the identity for bosons or for fermions. Okay. This is not p squared. Okay. This is just a single application of p. All right. But you can apply to the first function and you can apply to the second function. So applying to the whole function is switching the slots for the coordinate function, or which is usually called the orbital. So this is the orbital. Phi is known as the orbital part, and key is known as the spin function. All right, so orbital and spin. Okay, so you apply to the first and then apply to the second. But this thing here can produce only two things, +1 or -1. So for a boson, I can map what this operator does for the orbital part and what this operator does for the spinor part or the spin part, and I can make a table. So a orbital, a particle is a boson, spin, okay, and there are the possibilities, which is sign is plus. For the orbital part, you switch places of R1 and R2, and the function does not change sign. So this is a plus, but for boson, the whole wave function must be the same thing as switching places, but not inserting any sign. So if this is even for the orbital part, which correspond to an even function after permutation, produces only a plus sign. And if you have a minus sign for the spin part, you will not accomplish the goal for a boson, because for a boson, the whole wave function must be even. So if you have a plus sign in switching places here, you need to have a plus sign here. So this also is an even function, okay, by switching spins. And if you, after switching places of R1 and R2, you get a minus sign, which means the orbital function is an odd function. Okay, you need to have for the spin also an odd function, such that the multiplication of the signs cancel out. Okay, so this is for a boson. Okay, if the orbital part is even, the spin part is even. If the orbital part is odd, the spin part is odd. Okay, so this is a necessary condition for the spin statistic theorem to be satisfied. Okay, so for bosons this is valid. Okay, now let us turn our attention to a fermion, and we will discuss a little bit more for fermions. So for fermions, you have the same arguments, but now it's a fermion. Okay, for a fermion, if the orbital part is plus, for a fermion, if I switch places of two fermions, the function must get a minus sign there. All right, so you need to get a minus sign. So if this thing is plus, is even under the permutation, that the spin part must be odd. Okay, the spin part must be odd. And on the contrary, if this part is odd, the spin part must be even, because the product of the signs must always lead to a minus sign for a fermion. For fermions, the exchange of two fermions, switching places of two fermions, leads to a minus sign in the wave function. Okay, now let us write it a little bit more in details for fermions. You can do that for bosons. Okay, so suppose the following. You have two possibilities for the orbital wave function of two fermions. Suppose you have two states, possible states. I will call it A and B. So I have a function of a function of B. And I can put in the orbital a particle 1, and in the orbital B a particle 2. Okay. And also I can exchange the particles, so I can plug in orbital a particle R2, and in orbital B the particle R1. They are identical particles. You must remember that. All right, they are identical particles. I don't know if you can clearly see. I'll write it again. Seems to me that that part of the board is not so clearly, it's not appearing clearly. So suppose the following. I have the orbital part of the wave function, and I can write it as some orbital A. It could be a 2p orbital in an atom, okay, or anything. And I put here the particle 1. In the orbital B, I put the particle 2, but I also can do the opposite. In the orbital 1a, I can put particle 2, and in the orbital B, I can put particle 1. So there are two possibilities here in the middle, a plus sign and a minus sign. Now notice that if you exchange the labels under the plus sign, if I exchange 1 by 2, okay, I will get an even function here because it doesn't change sign. Notice that if you plug in R2 here and R1 there, and the same in the other term, the sign of the overall sign of this orbital function doesn't change. But otherwise, if you pick up the minus sign here and you replace R1 by R2 in both factors, you will get a minus sign. Okay, and also for spin, suppose a spin half particle. Okay, so for a spin half particle, I can have the following thing. I can have a four scenarios as a matter of fact, because if I have up state for the two particles, okay, there is only one possibility, which is this thing here. Both particles are up states, you can switch them, but the other term will be the same. So apart from a constant, it is this state. The spin state for down states or spin down states for both particles is the same. And notice that these two states here, if you switch the particles, you have a plus sign. It doesn't change the sign of the function. So this is the spin for particle 1. This is the spin for particle 2. Spin for particle 1, spin for particle 2. So if you replace, if you switch the particles, doesn't have nothing happen here, okay? And I have a third symmetric possibility with up and down states, which is the following: up and down, 1 and 2 for the particles, plus down and up, and this is normalized by 1 over the square root of 2. Okay, this is what is called the spin triplet. Spin triplet. It is symmetric under parity. Okay, this is symmetric under parity, the spin triplet. Because there are three states which I can construct with spins. There are three possibilities which I can construct with spins for a spin half particle. I'm considering spin half particle. For a general spin, I of course would write it in the following way: S1, S2 plus or minus S2, S1, and I can put a normalizing factor here. All right, so the general situation is the following here, okay? But considering a spin half in particular, which is far more important than any other fermion with higher spins, okay? Because electrons, protons, neutrons, neutrinos, and all the fundamental particles are usually spin 1/2. And as to the best of my knowledge, I do not know if there is any fundamental particle with spin 3/2 besides the composite systems. Okay, composite systems, it's okay, but for fundamental particles they are spin half. So this is why I'm particularizing to spin half. And there is only one possible anti-symmetric state, because if you try to anti-symmetrize with a minus sign here, two up spins, you have up, up, minus, up, up. This is zero. It's not a state which is of interest. Okay, zero, no particle. And down, down, same thing. But if you put one up and one down particle, you can plug in a plus sign or a minus sign. So the state with a minus sign is the anti-symmetric state, the only anti-symmetric state I can produce with two particles with spin half. Because notice, if you replace these particles here, you put down and up, you put up and down, you change sign of this thing here. This state is the only anti-symmetric under parity. It's called the spin singlet. Okay, this is the spin singlet. All right. So notice the following: if you have two fermions and you choose a minus sign here in the orbital part, so this is the orbital, and this is the spin. If you choose a plus sign here, if you choose a plus sign here for the orbital part, you will need to choose the singlet spin state. Why is that? Because if you choose the plus sign there, you will have a symmetric state for the orbital part. It adds constructively under exchange of the particles, switching places of the particles, okay? And in this case, it is the spin part which must be antisymmetric under the permutation. And this is only one, there is only one possibility, which is the spin singlet, okay? While by contrast, if you choose the minus sign here, you are choosing a destructive interference between the two parts of the orbital wave function. We are choosing the minus sign here. So the orbital part will be antisymmetric under permutation, and you need forcibly to choose the spin triplet, which is symmetric under parity for the spin part of the system. Now notice that two up spins add up to spin plus 1, two down spins add up to spins minus 1, two down spins, and the symmetric part up and down plus down and up is 0. So this spin triplet corresponds to a composite particle with spin 1. The total spin of the system is 1. While for the spin singlet, they act destructively, and the composite spin of the particle, this composite particle of two fermions, will produce a spin 0, okay? So the triplet is a representation of spin 1, and the spin singlet is a representation of total spin 0. But as individual particles, the two electrons are fermions, and they must have a total wave function which is antisymmetric under permutation. So if you choose plus for the orbital, you need to choose the singlet for the spin. If you choose minus for the orbital, you need to choose the triplet for the spin. Okay. And there is a very important aspect here which we can discuss. Suppose for instance you choose the orbital 1s. Suppose a particular case, A is equal to 1s orbital in a nitrogen atom, I can, or in a helium atom, because there are two electrons in a helium atom. Suppose A is 1s and B is 1s. Okay, so you have 1s for the orbital of the first electron, and you plug in the second electron at the orbital 1. Okay, 1 and 1. Apart from normalization, there is only one possibility of choosing the sign here, which leads to a non-vanishing probability. Because if you choose the minus sign here, you are just interfering destructively at any point of space, and the total probability of finding the particles in that antisymmetric orbital state, is 0. So in this case, both orbitals A and B are the same. You need forcibly to choose the symmetric state for the orbital. This way, the only possible choice for spin is the singlet, which means in the box for spins orbital 1s, you need to put one up and one down, okay? And this satisfies the Pauli exclusion principle, because one electron is in the state up and the other is in the state down, or the first electron is down and the second is up. But if you switch them, a minus sign will appear in the total wave function of the system, because fermions do that. The wave function for fermions must be antisymmetric. This is a very important issue. Now consider a second situation. Suppose you put the first electron in an orbital 1s and the second in a helium atom. Suppose the second in an orbital 2, it could be 2s, but suppose 2p x here, or projection minus here, okay? So you have a 1s for one electron, a 2p for the second electron, and this is 2p for the second electron. Now, if you have A and B distinct from each other, you could choose both signs. Okay, you could choose that. You could choose the plus and the minus. But usually, in this case, if electron 1 is in the orbital 1s in this example, and the electron 2 is in the orbital p minus, which I'll just write p, the orbital p, okay, you need to see that I can choose both signs, right? I can choose both, plus and minus. But if I choose a plus, it means that electrons at same places will add, the probability will add constructively. And electrons have negative charge. They will repel each other. And the Coulombic repulsion will increase the total energy of the system if they are more probably at the same position, because two electrons repel. If they are close together, they repel more and the energy increases. The repulsion energy increases. While if you choose the minus sign here, the two electrons at the same position will be very low. There will be a very low probability of finding them at the same place. As a matter of fact, if you choose the minus here, the probability of finding the electron 1 at the same position as electron 2 will be 0. Which means in the antisymmetric for the orbital, they prefer to be apart. And if the probability of both electrons being far apart is higher than for they being close together. And this scenario will reduce Coulomb repulsion, electrostatic repulsion between these two electrons. The energy will be lowered by this antisymmetric orbital, which is possible only if the two orbitals are distinct. Okay? If they are the same, you cannot do that, because if the orbitals are the same, probability will go to 0 if you choose the minus sign. So for the same orbital, the only possibility is symmetric for the orbital function and singlet for the spin. But for distinct orbitals, you can choose both. But the most favorable situation is the minus, is the destructive interference of finding the particles at the same place in space. And this is because you reduce Coulombic repulsion, electrostatic repulsion. But this way, you are led to choose the triplet, the spin triplet state. Okay, you need to choose the spin triplet. And the spin triplet means both spins up, both spins down, or in this spin zero projection, but corresponding to this representation, and a constructive interaction between the spins. All right? So this is a very important situation. All right? And remember from high school, if you are putting electrons for a given atom in a p layer, in layer p, suppose this is 2p, all right? The layer 2p, you will have the principal quantum number 2, the secondary quantum number or the orbital quantum number 1, m could be plus 0 and minus 1, and the spin could be up or down, or half and minus half. Okay? What you do, it is an empirical rule, or perhaps in a heuristic rule, which was found in chemistry, corresponding to, suppose you have two electrons. What you do to fill in these boxes in that atom? Suppose the atom has a this 1s2, 2s2, and this is carbon. Okay, I guess it's carbon. And you already filled in the 1s layer. The 1s layer is very lower energy. So even if you increase the Coulombic repulsion between the electrons, it is advantages. There has advantages for the total energy of the system to put two electrons there, because the nucleus attraction exceeds by far the repulsion of these two electrons. And the second layer, you start filling up the S layer. Okay, there is a so-called centrifugal forces, because higher angular momentum in quantum mechanics. So it's still advantageous to fill in the layer with lower angular momentum, so L equal to 0, so this layer is filled, and you are led to fill the P layer. Why not put both electrons here? So this is the minus, this is the 0, this is the plus for the magnetic quantum number. Okay, why not put both here? If you're filling this layer here, this is the 2p layer. Okay, this is the 2p layer for carbon. This is for carbon. Okay, why not? And the reason is that if you plug in the two electrons in the same orbital wave function, you need to choose the singlet for spin, okay, the singlet for spin. But remember, if they are in the same orbital, the only possibility is the symmetric or even combination of the orbitals for the orbital part. And this will increase the probability of finding the electrons at the same place, which increases the Coulombic repulsion. So what you can do, plug in one electron here, down, and the second in another state. They will be in this state here, a -1 for the total projection of spin angular momentum, and -1 for the total orbital projection. So this, since I am filling two distinct boxes, I am picking up for the A orbital a 2p minus, and this is a B orbital a 2p 0, because the projection of the magnetic quantum number is 0. Okay, so these are two distinct orbitals, and two distinct orbitals I can anti-symmetrize, which means Coulombic repulsion is reduced. But in this case, since the orbital part is anti-symmetric, the spin must be a triplet. It must be a triplet. Okay? And of course, y is down. I will not go into there because there are the Hund rules, which are empirical rules. They are demonstrated more or less in a mathematical sense also, but there are favorable states uh, corresponding to spin and orbital angular momentum interactions. There is a potential for that, and this is the more favorable situation. But of course, not mentioning not mentioning anything about more rules, If you know nothing, of course you could choose this state or this state or this state for this spin being symmetric. And of course you could fill this box and this box or this box and that or this and that. Okay, so there are more rules which corresponds to rules for lowering even more the energy of the system, which corresponds to something called spin orbit interactions. It produces more energy terms, which you could interpret as the electron orbiting the nucleus and the spin interacting with the magnetic field produced by the orbital motion. The electron sees the nucleus moving and producing some magnetic fields. This produces a spin orbit interaction. Okay, but in this scenario here, you need only to know that for fermions, wave functions must be totally anti-symmetric, and in this case, you are reducing the Coulombic repulsion. Okay, so far so good, I guess. And I see you next lecture where we'll start to discuss the fermion and boson algebras, right? Using annihilation and creation operators. Okay, see